Hey, everybody, welcome. In today's episode, we are going to be bringing on another show, and we're going to be diving into the wonderful world of Mark Norman.
Yep, we had Jake, our intrepid hazard class host, go a little deeper. The guy that you know, get to know him better.
All right, $5 says you can't remember the Cobra Kai motto.
It's a bad bet. Strike hard, strike fast, no mercy.
I'm always losing these bets. All right, but that actually sounds like the Viper that 908 just dropped.
Right, but instead of the roundhouse kick to the face, it hits the unknowns with FTIR and Raman.
And it sweeps the leg and reads the compound using the smart spectral processing.
And doesn't even need a gi or yell it and kick teenagers.
But it's still kind of badass. It's like having Mr. Miyagi right in your corner.
So check out the new champ at 908devices.com and have no mercy for your mystery chemicals.
You know, what really stresses me out during hazmat calls?
What, like everybody standing around saying, oh, this smells like a campfire, like our new candles? Mm-hmm.
Ooh, candles. Well, aside from the candles, yes, that's essentially what I'm talking about, right? Because they're guessing, it's not tactics.
Right. So Teledyne FLIR Defense built detection tools that we stopped doing that. Real sensors for real CBRNE threats.
They've been doing it for over 30 years. They've been helping first responders to actually know what they're dealing with.
Hazmat, Homeland Security, public safety, ugly scenes, clear answers.
Because there's no denying it. The more you know, the smarter you can operate.
So check out Teledyne FLIR Defense, any threat, anywhere, without mysteries.
And of course, as we promised, we were going to try our hardest to look into a battery solution. And while many companies have presented their product in front of us, there's been only one noteworthy one because it actually extinguishes the lithium-ion battery fires. It works on multiple classes of fires, prevents fire spread, and it keeps the lithium-ion batteries themselves from reigniting.
And before that guy with the keyboard warriors, let's cap lock asses for proof. The links are in the show notes for the UL Class A and B, as well as the BSI for 10 categories, including lithium-ion batteries.
On top of all those testings, we've put it through our own field tests, and I got to tell you, we were really impressed with the results. But we always suggest that you do your own myth busting. It's available in a variety of different options, so it can integrate with whatever process you're currently using. You can access more information by checking out Fire Suppression Solutions, or click on those show notes in the links. Click on the links in the show notes.
And now more of the show.
Welcome to the Hazard Class Podcast. This is the podcast where I ask my stupid questions to some of the smartest people in and around the world of emergency services. My guest this week has a PhD in analytical chemistry and for over 20 years of experience in chemical detection. Formerly a senior field application scientist with 908 Devices, he played a key role in developing portable technologies for hazmat teams, and his expertise has shaped the field of hazardous materials detection as we know it. Today, we'll discuss his career, the evolution of chemical detection, and what the future might hold with my guest, Dr. Mark Norman. Mark, thank you for joining me this morning.
Hey, Jake, how you doing, buddy?
Good, real good. Yeah, I appreciate this. This has been a long time coming. This might have maybe my longest running trying to get a podcast with someone, and it finally worked out. And it was for no fault of anyone's own. It just was a scheduling thing. We've been probably trying to work on this for darn near a year.
It's been a while. I know we even talked back at IAFC, and between the two of us, it's been tough. I will say, you have some of the smartest people in the business on your podcast. I'm not sure if I fall into that category. I'll do my best. You really raised the bar there.
Yeah, I think the PhD gives you pretty solid credibility.
Well, I've said this many times, Jake. Having a PhD doesn't necessarily mean you're smart, but it does mean you're patient.
Yeah. Well, so what is so? I was trying to even read about it. And, if I'm being truthful, I'm not smart enough to even understand what your PhD is in. Yeah. Right. So let's go to that. Like, you did your doctoral dissertation on what?
Okay. So let me step back a little bit.
Okay.
To lead up to that, but how I got into chemistry.
Let's do it. Yeah.
And then specifically analytical chemistry, which in the simplest terms is measurement science. Okay. How do you measure things? Mm-hmm. But when I was a young lad, actually a sophomore in high school, I grew up here in West Virginia, grew up on a holler, as some of your listeners may be aware of, and was always kind of a curious kid. But when I was in high school, my chemistry teacher at the time, Willie McLean, God, I remember him. He was one of these real gruff, he was old at the time kind of people that a lot of people kind of didn't mix with, but I just gravitated toward him. And there was a lecture he gave early on when he talked about how sodium, is a very water reactive element, metal, so much so you have to store it under oil in the lab so it doesn't blow up. And then chlorine, one of the most poisonous gases, was used as a chemical warfare agent back in World War I, and these highly toxic things, and you mix them together, and what do you get? And he puts on the table, table salt. And I said, man, that is cool. Yeah. That's chemistry. And that really kind of struck a chord with me in terms of chemistry and science. By the way, this same professor also did a lab every year where we burned sulfur. And I really don't know what the point of that was, other than to piss off the entire building, because you can imagine the smell. Yeah. But nevertheless, I really like that. So I wanted to go into chemistry. Actually, when I went to college my first year at West Virginia Wesleyan, I was pre-med. I thought I was going to be a medical doctor, and I wanted to be the first doctor in my family, and really the first out of the community where I grew up here in North Central West Virginia. But I took one semester of biology and said, screw that.
Not for you.
Too much memorization, too many cycles and all this stuff you got to learn. But chemistry was exciting, so I got into that. And then as I got further in my college career, my advisor gave me a project to make this very simple little contraption where it was basically electrophoresis, where you apply an electric field. You basically hook a battery up to a mixture of chemicals, and they separate in some goo, and you measure the different colors that come out at that time with a UV vis little spectrometer. And I thought that was really cool. So I said, well, analytical chemistry, measurement science, as my advisor described, the nuts and bolts of chemistry. You get your hands dirty and you build these contraptions. So where was I going to go? Well, the only place for me was the University of North Carolina at Chapel Hill, because I've been a Tar Heel fan since I was a little tyke, and watching the NCAA tournaments in my bedroom when I was 10 years old. So I got into UNC. There was a professor there, Dr. Roger Miller, who was doing some really interesting work with spectroscopy, which basically is how light interacts with stuff or matter. And as we'll talk throughout my career here, how spectroscopy and infrared and Raman in particular have become so prevalent and important in the emergency response space. But this project was using infrared and in particular FTIR, which a lot of your listeners will be familiar with, relative to like the hazmat ID, the True Defender from Thermo, and other types of FTIRs for identifying solids and liquids. More recently, the Explorer, which 908 came out with to do gases and vapors. That's FTIR, but we were applying it to aerosols, which are particles suspended in a medium, in this case air, and looking at aerosols under conditions mimicking the upper atmosphere of Earth, the stratosphere. And the reason for that was the way climatologists do modeling to look at things like global climate forcing and climate change, which we all have heard of, is they need to incorporate not only the gases, the greenhouse gases, and things of that nature, but also the aerosols, the particles in the atmosphere, to learn the impact they have. And there was no real data under those upper atmospheric conditions at the time. This is in the late 90s. So that's what my project was to characterize these particles. Specifically, they were sulfuric acid, nitric acid, and water, and all in various combinations at temperatures approaching 200 Kelvin. Which is pretty darn cold, and using a combination of FTIR, but also infrared diode laser spectroscopy to probe these optical properties. So my thesis is titled Infrared Spectroscopic Investigations of the Complex Refractive Indices of Stratospheric Aerosols. Say that 10 times real fast.
Yeah, I giggle as you say that because obviously it's a very impressive thing. And prior to us starting to record, I made a comment about it's really nice to talk to someone that's much, much smarter than me. You're like, oh, no, I couldn't spell half the words in the sentence, let alone write a thesis on it. But so are you using then like weather balloons and stuff to do measurements in that atmosphere, or how are you getting up there? Obviously, somehow.
Well, that's a good question. The short answer is we didn't get up there, quote unquote. And this is where the analytical chemistry, the nuts and bolts, really appealed to me. Is we built a chamber for the lab, which was temperature controlled, humidity controlled, so we could mimic those conditions of the upper atmosphere, and then generate the aerosol particles under those conditions, and then probe them spectroscopically, because the data that had been available to date, again, this was at the time, late 90s, were all at room temperature. And we did find, and I was able to publish a few papers, that the conditions of the upper atmosphere really changed the chemistry, specifically the ionic equilibria that occur within these acid solutions at those conditions. So it was pretty cool work. Got to really get my hands dirty. Probably collected about 6 weeks worth of data in 5 years. Most of my time was rebuilding pumps and realigning this giant interferometer. I've told some of the folks I've worked with in emergency response over the years who look at, again, something like a hazmat ID going back to the early 2000s and the other devices that have come out. Oh, this thing's big. You should have seen the FTIR I worked with.
Yeah,
room it's not
size,
the size
maybe?
of a refrigerator, if not more. So yeah, it was that. We just mimicked those conditions, got a lot of cool data, and I knew I wanted to work in the field of spectroscopy. And infrared spectroscopy was particularly interesting to me because, as most of your listeners, if not all, will know, you can use it to get molecular chemical information, and I thought that was the bee's knees, and so I sought out to find a job and got lucky enough to be placed with a small company called Sensor Technologies, or Sensir, based in Danbury, Connecticut, back in July of 2001. And so that's kind of a quick summary of my academic career and how I got to where I was and what I did. Still a diehard Tar Heel fan. Watched my Heels play basketball all throughout the season, but very proud to have been able to do that work at such a prestigious university, and then have the career that has followed since then.
Yeah. So here's my first dumb question, right? Because there'll be a bunch. If theoretically aerosols are lighter than or heavier than atmosphere, like how are we getting these aerosols to that level in the inside the stratosphere?
Yeah. So what happens is they are heavier, but depending on their size, which is measured in microns, they can be suspended in, we say the fluid medium, it's air, for a period of time before they would settle. And what happens is these aerosols in the upper atmosphere can form just because there's maybe just dust particles, and these gases and vapors can sort of cling to them and then form these little particles. They can be spit out by volcanic eruptions. And there's a lot of different ways that they can stay suspended until they get too big, and then they start to fall out and settle. But what the scientists do, I assume they still did at the time, was they'll do measurements like fly planes through these clouds and collect in situ or data right within the clouds, and then model it using the data we produced in the lab. So yeah, the aerosols, depending on their size, again on the order of microns, can stay suspended for some period of time and until they decide to drop to the ground because they get too darn big and heavy.
What's that period of time look like? I mean, are we talking like years and years, or are we talking like hours, days, weeks?
Depends on the condition. It could be days, weeks, months. It really depends on the conditions in which they're formed. Think of things like flow, airflow, how high up they are in the stratosphere. So all those conditions go into how long they persist, which is kind of the term we use for how long they hang around. And then, of course, you have others being formed sort of continuously.
Yeah. So let's go back to the beginning, though. What did your parents do, and what did they think of you trying to be this high achiever, to be the first doctor in your town?
Well, I will tell you, I grew up in a very loving, very strict military household.
Okay.
So my parents, they both grew up dirt poor in West Virginia, but made something of themselves, very blue collar. My mother was a teacher's aide within the school system and was very successful doing that. My father, though, devoted his life to the West Virginia Army National Guard. Spent 26 years in service. As a result, I have always been had a place in my heart for soldiers, for the military, and in general for responders, just because I saw, my dad throughout his career and what he did and how he devoted his life to that. He did logistics and military management.
Okay.
So you can imagine what our household was like.
Yeah, I'm sure it was pretty
very sweet man. Don't get me wrong, but very by the book. So now I actually did want to serve because my dad was the youngest of 10, and he grew up. He was born in 1942, and he was the youngest. Like my grandfather, his father fought in World War I, and so all of my dad's brothers served. So I just felt, I'm the youngest of 3. I have 2 older sisters. So as the young boy, the young pup, as my dad called me, that I would follow the lineage and serve as well. But I was born with a congenital ear problem. In my right ear, I had a lot of issues, which has led to permanent hearing loss. And basically, my dad said over the years, well, you can join, but you'll never pass a physical. My dad did have a little bit of a Appalachian accent. So I said, okay, well, if I can't serve because of this, this physical problem, what can I do? He did encourage me to pursue my academics, and because I got into sensor technologies in 2001, and we can talk about how that evolved into getting involved in this emergency response field. I feel, Jake, the only word I can use is just honored and privileged to have been able to, if you will, serve in a way by helping so many firefighters, law enforcement officers, soldiers up and down the board, all across the world, with using this equipment in the field the right way, training them, listening to them. It's truly been an honor to be able to do that. So that's kind of how I've tried to give back, is just take my skills and help, those brave men and women on the front lines do their jobs a little better, a little more safely every day. So yeah, that's kind of my childhood and how I got to to doing the type of work I'm doing now.
Your parents have since passed?
Yes, my mother passed away in 2016, and my father passed in February of 24. Yeah.
Oh, sorry to hear that.
No,
but they were able to see you become a doctor. What did they think of that?
Yeah. Well, they were pretty happy. They were pretty happy. Like I said, I wanted to be a medical doctor. But then once I decided to go the PhD route, they were just thrilled. And it's funny, my dad, typical, proud father, anytime he would introduce me, to someone when I'd come visit, say, this is my son, Mark, he does analytic chemistry. He didn't even know how to pronounce it. God bless him. So I'd always have to kind of have my little spiel for what I do, but tremendously supportive. Both my sisters, tremendously supportive as well throughout that. And just really pushed me. The other thing, I want to go off on a little bit of a tangent here, Jake, that actually has been tremendously helpful to me in my career, but it relates to how my parents encouraged me, but also kind of pushed me. When I was also in high school, the same year I learned about the magic of sodium chloride, my mom, who worked in the school system, strongly encouraged, is the phrase I'll use, me to try out for the school play. Anything Goes, this lavish Broadway musical that they did at the high school. And so I got a pretty big part in the play, did it. Fast forward, when I went to West Virginia Wesleyan, majoring in chemistry and minoring in math, I also had a partial theater scholarship. And so I was very active in dramatic arts. You see on my background some of the, to either side of my Carolina diploma, some of the posters from some of the shows I was in. And it really gave me confidence in the ability to be in front of an audience and to speak clearly and to do all those things you need to do as a presenter. And that combination of being a scientist, but also a performer in a way, has really served me well in the type of work I've done over my 24-year career, where I've been in front of very large groups. I've said many times, because I'm actually kind of shy, believe it or not. I grew up really shy. I'd rather be in front of 1,000 people I don't know than beside a stranger on an elevator. Yeah. I never know what to say.
I understand that feeling exactly. Holy cow, do I ever.
Yeah.
It's a super funny thing that you would bring that up, is because, people that know me, inside my little circle, I'm outgoing and stuff, but man, to the world at large, I am pretty reclusive. Yeah. People would never guess it based on the idea that, I teach all over and I have the podcast but yeah, it's very similar. I did some plays back in the day, and then I was in a band for a few years, which kind of shaped my ability to, put myself out there. So it's kind of interesting. We have a similar thing. Were you a song and dance man? Were you singing and dancing and stuff too, or what?
I sang. To say I danced is probably a stretch. I did what I had to. Yeah. Never really liked musicals. I like what they call the straight plays, where it's just you on stage. But that's another thing my dearly departed mom had me do. She had me do speech contests. Again, this is in junior high. She had me to sing in front of the church. Just anything she could do to get me out of my shell. Yeah. And thanks, Mom.
Yeah. It seemed to work, right?
I appreciate her. for it, where dad was more of the, here's how you invest your money. Here's how you, manage this. Here's how you fix this. My dad also made his living as a carpenter for many years. And so I learned a lot from him just about hands-on, things like that and using tools and building stuff. So maybe that's why analytical chemistry also got into my blood. So anyways, that's a little bit about me.
So let's go back to that first moment, because it actually ties into a question that I would love to talk about. And maybe there's a good answer, maybe there's not. And maybe it's an answer that would take an entire podcast. So maybe we could cut it short. But so we talk about like sodium and chlorine makes sodium chloride, which is table salt. There's also the other big one, which is like H2O, right? Hydrogen, oxygen somehow makes water.
Right.
Why is chemistry so confusing?
I don't think it's confusing.
I bet you don't. But if it in the world of chemistry, it does not seem all too often that A plus B equals, AB, right? Or 1 plus 2 equals 3.
Right.
Why?
Yeah. Electrons.
Okay.
There. All right. So
moving on.
And
that's
we'll see you again. No.
Yeah.
First of all, you talk about chemistry and I that's how I did get sort of the spark. When people hear I'm a chemist, and I'll get questions like, I have stuff under my sink. What happens if I mix, this with that?
Yeah.
I'm an analytical. I can measure what you make. I'm not an organic chemist, and I have to explain. It's like your doctor. You don't go to your cardiologist for something on your skin. And we all specialize. Having said that, Jake, it's about electrons. And in college, my organic chemistry professor talked a lot about how electrons matter. It matters what they do. So it can be confusing because, like you said, you take two things, let's just say two, with very distinct chemical physical properties and put them together, and all of a sudden there's this whole different thing. It doesn't make sense. It almost becomes philosophical.
Yeah.
But the reality is that in chemistry, and we hopefully understand the basics that we have the electrons, which are those energetic particles that surround the nucleus, the protons and neutrons. We don't worry about the protons and neutrons in the type of chemistry we do. We don't do nuclear chemistry, at least in terms of what we're describing. But what those electrons, those little particles that dance around outside in those shells, we call them, those areas around that little tiny ball in the middle, what they do, and more importantly, what they can do is what it comes down to. So think about a ball, and then it's surrounded by these sparky little particles. If one of those sparky particles really wants to jump away and then go to another ball that really, really wants a sparky particle, then that's going to be a pretty reactive chemical process. Whereas if you have, take something like water, so the oxygen, boy, its electrons are there, but it's missing a couple. It's like, man, I'd really like to have a couple more electrons, and then I'd be nice and safe. And then here's hydrogen going around. Well, I got one. There's another hydrogen. Oh, I got one. Okay. And then they come together. And there's something called the octet rule in chemistry, and we don't have to get too deep into that, but think of those things on the very right side, right? Those noble gases. When those electrons in that outer shell, when they're nice and cozy and happy, things tend to be pretty calm. So it's about what the electrons want to do and can do that result in those processes occurring, and then those chemicals existing that, let's just say, have much more benign properties compared to maybe the properties that are a little more scary.
Yeah.
When they're just pure elements.
There you go. That's from a first responder perspective, it becomes weird though, right? Like, and like, obviously that's a perfect chemistry answer. It's a how it works if you can know all the things and understand them. But now, you take a firefighter or a police officer or someone that's going to work in the hazardous material space, and don't get me wrong, there's a gradient scale of responders, but the average first responder understands the equipment they have, the PPE they have, and they're not really getting super deep in valence electrons or whatever it might be, right? And so when you are that person, then now it becomes witchcraft, right? It's like, wait, sodium and chlorine, now we mix those together, we have table salt. And so it becomes this like, well, you just have to memorize the idea that hydrogen fluoride's bad, right? Like, because, fluoride's good for your teeth, but when you mix it with hydrogen, all of a sudden it kills you right away, right? It's like there's not a good, clear path other than just knowing kind of the target hazards inside the world.
Well, and that's why we have the NFPA diamond. That's why we have GIS hazard symbols. Responders, firefighters, law enforcement officers, soldiers, they don't need to know all that stuff. Like you don't need to know how an internal combustion engine works to drive your car. Yeah. You just need to know how to push the pedal and push the brake and do the things properly. That's why we have those symbols to indicate very quickly, okay, what's the bad thing that this stuff can do? But I think there is value in an appreciation at an awareness level that, chemistry as a science, as a process, can produce some things that can be pretty harmful. Explosives, another good example, especially nitrate-based explosive. The reason they go boom is you have those nitrate parts. Let's think of something like TNT, trinitro. Boy, it really wants to not be that. Yeah. It does not want to be. Remember, I talked about electrons, what they can do and want to do. It doesn't want to be that. So when we see the hazard symbol with a big, it looks like a bomb exploding, we go, okay, we got to take some precaution with this. But then the value of our measurement technology, whatever it is, whether it's simple air monitoring, gas monitoring, all the way up to chemical identification, and even some more sophisticated types of analytical approaches. All that does is just tells us, okay, what are the hazards we're dealing with, and then how do we proceed? What hazards are not present, right, Jake? So ruling hazards out is equally important. And if it's a little more complex, what is this chemical? And then we have research. That's what research is for. Say, okay, I found the chemical of this name. Here's the CAS number, maybe that social security number for the chemical. We call it the CAS number. Look it up. And I, even as a scientist, Jake, I don't pride myself on all the things that are up here. I actually don't memorize a lot of stuff. I pride myself on being able to find the information. Right? Yeah. Where do I get? Whether it's Googling it, whether it's pulling out a book or talking to someone who probably knows. So most important thing, I think, for responders of any type when it comes to chemistry is know how your equipment works, whatever that equipment is. Know the do's and don'ts. So make sure you're getting reliable results, and then know where to go for the information you need. Don't worry about being a chemist and worry about electrons and orbitals and all that stuff. That stuff's great. That stuff's for people like myself and others who can then take that information and then ideally put that information into formats that are useful. That's what you see in things like software on some of these more sophisticated devices. Try to make it useful.
And that's what I was going to say. And that is something, obviously, you're no longer with them, but 908 device does an unbelievable job of taking extremely high level information and bringing it down to the first responder level. I mean, it is like the screens that you're seeing on these 908 devices are like chef's kiss. You can't make it any more simple, which has been Beautiful. So talk to me about that process. Obviously, we're going to go and do a whole history of all this stuff. But since we're on the topic, you know, that user interface is so important. And some of the devices, frankly, just fail. Like these companies are making devices and, you know, while it's beautiful technology, it technically works. If the user that's using it can't use what they're seeing, it's functionally useless. But 908 devices always seems to do a really great job of portraying that information. What goes into that process, and like, how do you achieve such a high level of that compared to the rest of the market?
Well, I will say that 908 Devices is doing some amazing things. I stepped away not long ago just because the travel burden was kind of getting on me. I've been to 24 countries in 24 years, Jake. I just counted up not long ago, and I'll be 52 soon, and it was starting to take its toll. What they are doing there, especially as what they call 908 Devices 2.0, that's a public thing that they had put out, where, you know, incorporating the formerly red wave, you know, technologies with the optical, infrared, and Raman is pretty impressive. I will say that getting user interfaces to where they are today, it's been trial and error. Now think about this. I go back to when I started my career in 2001 in July, and this little bit of history is germane to your question.
Yeah.
We at Sensor Technologies had this device called the Traveler, or Travel IR, and some of your more seasoned listeners will be familiar with it. It was not designed for emergency response. It was the first portable FTIR, but it had a separate laptop. It had a streamlined user interface, but it wasn't designed for like a firefighter or even a soldier in the field to use effectively. So we set out at Sensor. This is all after 9/11 and the post 9/11 anthrax attacks and the white powder scares, and there became a clear need for chemical identification technology to supplement the basic air monitoring and things that were already in the field. We set out to develop the Hazmat ID, which came out in 2003. But in the interim, we developed a much more simplified software interface called Hazard ID. And we did it working with some firefighters that were consulting with us, who looked at what we had and said, yeah, this is too complicated. Here's how a firefighter thinks, right? And I'm just using firefighter as a general, but responder or any person in the field who is dealing with chemical hazards but is not a chemist. Let's just try to keep it to that sort of definition.
We're simple people. It's okay. We know who we are.
Green is good. Red is bad. Yellow, okay. Big button. Very few words. These are the types of things that we heard. So we developed this little interface in the interim, and then we had the Hazmat ID. But then with the Hazmat ID over the years, you learn, well, this is too complicated. Some people like to look at graphs. Some people don't. Okay, let's put that function over here. In parallel with that, Ahura Scientific, which was eventually purchased by Thermo, Sensor Technologies in parallel was eventually purchased by Smiths Detection. But then Ahura/Thermo was doing some really great stuff with Raman spectroscopy and doing some interesting things with algorithms, so applying some pretty complex math to the data, the spectral data, to produce results with green screen, blue screen, red screen, compared to the Hazmat ID, which required a little more interpretation. And so that evolved. This was in the mid-2000s. And then you sort of fast forward to where 908 Devices is, and the 908 Devices of today represents, it's really kind of interesting. The core group of people from Sensor Technologies, going back to my early days, and the core group of people from Ahura Scientific now together as 908 devices. So you really have the most innovative, the most progressive types of scientists, engineers, working on this stuff who have learned over the years. When I did a workshop last year talking about the evolution of technology, and one of the last points I made is we know you better, Mr. or Mrs. Firefighter. 24 years later, we just know better. So, and I'd say there's still room to improve, but just learning how, if you look at the interfaces of things like the MX908 or the Explorer or the Threat ID or any of those other types of 908 devices products, and even some of the other products that are out there where big buttons, simple buttons, colors, and again, it's not to belittle. It comes from an understanding that when a responder is in the field, pushing buttons and making this one measurement is not the only thing he or she has to do. They are also using other meters. They are listening to incident command, right? They're giving information back to the IC. One of the most humbling things I heard, Jake, this was a few years ago. I was doing a training with some special forces folks. And we were talking about and I won't mention the product we were training them on, but we were talking about, okay, when would you use this particular product when you're going on scene? And in this case, they're talking about, well, if I'm making a kinetic entry, meaning I got my rifle, and potentially into a clandestine, cave where they're maybe making something nasty. He said, I got my rifle and I got my JCAD. And I think everyone's familiar with the JCAD. That's the wearable personal protection device for the chemical agents. He said, because my first priority is to not get dead.
Yeah. Yes.
Right?
Yeah.
After that, once I've cleared, then I can take the device you're talking about and come in and start making measurements. So it's really that humbling appreciation that, and I've even said this over the years, firefighters don't just use a hazmat ID or a protector or explorer. They also use axes. They use jaws of life, depending, unless you're a dedicated hazmat team. So it's that appreciation. It's also just the evolution of what's available in terms of software development platforms and user interface technologies that have led to what you see today, where it's very simple. And I've also said this, I can't wait. I hope I'm around another 25 years to see where things go. So yeah, that's where we are.
So
today's episode is brought to you by Rigaku Analytical Devices, who are the folks who've been practicing and perfecting the 1064 nanometer Raman longer than most of you have been doing hazmat.
They just launched their fourth generation handheld analyzer, the Icon X, built specifically for real-world stuff that the hazmat teams have to deal with. We're talking about dirty powders, mixed materials, dyes, colors, all the things that throw our instruments into a temper tantrum.
1064 nanometer laser means reduced fluorescence, so you get fast, reliable chemical IDs in under a minute instead of staring at a blank screen wondering what's going on.
And it's not just new paint on an old model. This is a new platform. It's not just an upgrade. It is an entire toolbox. It supports new accessories, includes standoff analyzations. That way you can get answers without having to get too close.
If you want an analyzer that has been evolving right alongside the hazmat world, check out Rigaku's newest Raman at rigakuanalytical.com. And take a look around you. How many lithium-ion batteries you got around you right now?
I got 6.
Everywhere you go, batteries are everywhere. Departments are starting to deal with them, and they're doing it on a regular basis.
Yeah, that's why we're excited to tell you about a new product that is proven to limit and control battery fire propagation. It's from a brand called DeGeo, and it is chock full of hazmat experts who know that there's a better way for us, the first responder, to store, handle, and ship at-risk lithium-ion batteries.
This product will solve your lithium-ion battery problems. It's lightweight, it works across all battery types, and we can say it lives up to the hype because we tested it firsthand.
It's called a Bexian FR, and it's part of a 2-part system with a scientifically designed granular along with a UN-certified paler drum. The most important part of Obexi and FR is it's proven to reduce the toxic ideal H gases that are being emitted when these batteries do their thing and kick off. So ultimately, it's going to help keep your team safe.
So to go learn more, go to thehazmatguys.dgeo.com. That's thehazmatguys.dgeo.com. Let's get back into this.
So if that's where we are now, and there's more to talk about in there for sure, but talk to me about the state of analytical chemistry, or rather maybe the measurement or the field measurement for hazardous materials when you entered the job market.
So when I entered, you're talking about in 2001.
Yeah. What was possible for a hazmat team to identify at that point?
Yeah. So 4 gas, 5 gas meters, right? Rad detection, right? PID if you were just using a 4 gas. Papers.
Yep.
There was, in terms of analytical, more sophisticated analytical devices, the a GC mass spec called the HAPsite, which really had been developed by Inficon more for environmental type of applications, but there were some bigger, FDNY being one of them.
Were they huge? Much bigger than what they have now, I would imagine?
Well, they're pretty much the same size as they are now. I know they've made changes, evolutions over the years, but so you basically had very simple entry tools, right, to rule out, to detect hazards, and then you had GC mass spec.
Yeah.
So there was quite a chasm there in terms of availability. And again, in the wake of the anthrax attacks, there was a concern about bio detection identification. So, but there really wasn't anything more. I would put in qualitative chemistry, the HazCat kits. They certainly were there, certainly more popular in other parts of the country. I know in California and out west, that's where they originated. But as far as electronic analytical systems, they just didn't exist for chemical identification. And again, Sensor Technologies had this quote unquote portable FTIR. And we started getting phone calls that are at the office in Danbury, Connecticut in late 2001. Actually, some of the first calls were, "Hey, can you identify anthrax?" Makes sense, right? Because we as a business had tried to be in touch with the hazmat community. We had no idea. We didn't know anything at the time, but we had some contacts in that space. So we started getting some calls. And our short answer was, nope, can't do anthrax. And that's a whole other podcast topic, just biologicals for spectroscopy. But we said, what about the things that aren't anthrax? And as I'm sure you're aware and your listeners are aware, most of those white powder calls, they weren't anthrax. They were other stuff. We can do that. And so one of the most useful things we did as a business, this is now in 2002, was we went to the local grocery store, pulled every white powder we could off the shelf, and built a library of about 40, 50 items, and just put it on the system as the white powder library. And that became very, very valuable. Again, listening to the operators. So it started to fill a gap very quickly for chemical identification. The other side, Jake, is not a technical one. The other side is the financial one. So why did hazmat teams have a 4-gas meter, an LEL sensor, an O2 sensor? Were they developed for hazmat?
Confined space, right?
Confined space,
from
right?
Industry.
From mining. I mean, it's not like someone sat down and said, "Oh, for a hazmat call, we need to build this little meter." They said, "Well, what's available? pH paper? Well, we've been using it in the lab for years. Let's use that, right?" And all these other papers. It was just using what the hand-me-downs were, from the chemical response world.
Were you doing colorimetric tubing at that point too?
So we as a business were not, but there were some colorimetrics out there for sure. And because I remember early on hearing people talking about the pumping and getting the right number of pumps and making sure you get the right color change. But again, all very qualitative, all very simplistic in terms of the information provided, and not very specific. So there was this need, but then it wasn't until the federal government, again, post 9/11 and post the anthrax attacks, started flooding the response community with funding, with grant funding, that an agency could afford to buy a $50,000 meter. To do something with. And again, only a handful of agencies had the GC-mass specs. And I remember doing a demo early on down at FDNY who had a GC-mass spec. And there was a gentleman there who since retired, but he was sort of their meter guy. And I said, yeah, well, the GC-mass spec, it works, but it's hard to keep people proficient on it. And then we come in with a Traveler and we run gasoline as a sample, and it comes up, 87 octane gasoline. And they go, oh, that's great. I just want to know it's gasoline. And I just want to know it's flammable. And it's nonpolar. I don't care about the 500 components in gasoline. So that now goes back to your earlier question about what information is valuable.
And that's been the biggest problem with that. Like, we have a GCMS, right? We don't like it because it doesn't give us usable information, right? It's like, it's really difficult to keep people trained up to using it proficiently, especially in real time under real circumstances. And then after you spend all the time to do it, the thing it spits out is basically needs to be sent off to be analyzed and made usable. And so you go, awesome, we have this unbelievable piece of technology. I respect it for what it is, but functionally it doesn't serve us a purpose, right? And now we have obviously some other tools which are more helpful, but it was such a bummer. We got it. We're like, this thing's going to be amazing. And then all of a sudden you actually run it and you go, okay, well, that's a long list of things. And I don't know if any of them are particularly helpful, unfortunately.
Yeah, well, I will say this. So in my, if you will, current role, stepping out of the industry per se for a while, I do have a consulting business, and one thing that I'm passionate about is training and educating users on this equipment, because I have an appreciation for what you just said. Look, if you're a lab chemist and your job that you're assigned is to run samples on a laboratory GC-mass spec, you go through a lot of training, you have protocols written, that becomes your job, you do it every day, you become proficient. You don't just walk up and start doing GC-mass spec measurements. GC-mass spec is an amazing analytical capability. I mean, as far as GC-mass spec for the field, they've really come a long way. Again, you have to go back 20 plus years ago. Where it goes from here, who knows? But to your point, unless you are trained and maintain proficiency, it's very challenging. And then, Jake, I think about going into workshops and classes, especially with younger, when I say younger, the newer responders in the field, we're still talking about how to interpret O2 readings and how they correspond to LEL readings, right? And cross sensitivities, and how certain things like propane, for example, can give you a reading on your CO sensor. So this is down and dirty basics. Now, do we expect in large part responders to be doing GC-mass spec? It's a challenge. So my point in all this is, I hope that across the board responders can have an appreciation for what all these technologies can do, but stay in your zone, right? And become very, very proficient in what you do use every day, right? Whether it's a 5-gas, 4-gas PID, what have you. There are a handful of the meter guys who will get into the GC mass spec. But it's just like in any other field. You have a larger number of people who do the basic. It's like you go to the doctor, okay? You have symptoms. I don't feel good. What's the first thing the doctor does? They don't send you for an MRI. They take your temperature, right? Take your pulse ox, take your blood pressure. Those are your initial readings, your site survey, as it were, your recon. Okay, trying to rule things out. Okay, well, you might have strep throat. Well, let's do a strep test. Now, that's a presumptive test to see if you have that. That's kind of your next level of analytical capability. Okay, well, this is a pretty confusing thing. Now we got to do an X-ray, maybe an MRI. Now you have the more specialists. They don't do that at the doctor's office, the MRI. They send you off to a place where a trained specialist. So there are places for all of this. I'm not sure that by and large, the hazmat community, is set up where GC mass spec and those much more sophisticated technologies have a large role to play, just because of the structure and because of the turnover and because of the terms of turnover of teams and just all the other training requirements. But there is a place, and one thing I seek to do is to at least provide awareness and education on this type of thing, and if I can, be of service to train people and to to in the end leverage everything you have. Most importantly, to do your job more efficiently and to keep you safe.
Yeah. So. I'm interested to think about like the landscape that we have now versus what we could potentially have in the future. Like when, historically, I feel like the notion was focus more on classification than identification, because if we can get it in one of the 9 hazard classes, we can probably deal with it. Right. And now I wonder how much of that thought process was the idea that we just didn't have the ability to necessarily identify things. Well, if it's a flammable liquid, that'll do, right? We can deal with it. And now with these emerging technologies where we can identify things instead of just classify them, how do you think that's going to change hazmat response? And like, where does it go from here?
Yeah, it's a great point, Jake, that you go back to the early days of hazmat, the late 70s or so. You used what you had. So, to your question, well, do we just seek to classify because that's all we can do? Now you fast forward to 2025. Now we have all these other tools. We have infrared, we have Raman, we have GC mass spec, and you're going to see some other stuff coming out, I'm certain, over the years for all phases of matter. Are they coming out because we need that? Well, I would say yes. I would say as threats evolve, and we've seen this in recent years, where look at the Novichok situation. Once that became declassified, those fourth generation chemical warfare agents from Russia, and the state and local teams were made aware that this potential threat exists. Okay, you need something to identify that type of newer threat. And I'm sure threats will continue to evolve. So I believe there is a need for more sophisticated technology in this greater response toolbox. It really depends on your jurisdiction. It depends on your mission. It depends on your training and your training requirements. But I will say this. Ain't nothing ever gonna replace pH paper. Ain't nothing ever gonna replace fluorine paper, oxidizer paper. Why? Look, even chemists in the lab with PhDs, we need to know the pH of something. We might use a pH meter if we need to know it's pH 8.2. But if we just want to know if it's acidic or basic, just get some litmus paper. We use it. Why wouldn't you? So it's certainly, I don't think, a replacement of any of that classification technology, because qualitative chemistry and quantitative chemistry are all parts of what we do in the lab. Why wouldn't it be part of what you do in the field? Now, having said that, if I may, Jake, I think if we look forward to where things, I hope, will go, it's making things more holistic and taking the information from all the various and I'll say technologies, not necessarily meters, and putting that together. And I'm certain that with the advent of AI, that you will see this evolution take place in probably not too long from now, where a responder in the field can say, okay, I got this reading, this reading, this reading. Ideally, these readings are, fed back into some box, this smart box, which processes it and says, not only here's what the threat is, here's all the information you need, and not just spit out a safety data sheet, but actually give you tactical information decision-making. Because all this stuff is great, Jake. All these acronyms, all this technology is great. We cannot forget, in my opinion, and I think you'll agree, and I'll ask you this question. When you're on scene, what are your priorities? What is your responsibility?
Yeah. Right.
Number one.
Life safety, right?
Exactly.
This is what I'm worried about people not dying, and then we're worried about getting things back to functional.
Exactly. You got to keep yourself alive, because if you're not alive, then the public can't be helped. Keep the public safe. Property, you just want to mitigate, whatever the hazards are. And it's really comes down to safety. So what tools do we need? What information do we need to render something safe, whether it's at a residential complex in a cul-de-sac neighborhood or out on the battlefield, somewhere, in a theater of war, or at a border crossing, whatever the situation is. What can we do to take all these right now, which I see as still kind of disparate gadgets and information, and put them together? And again, I believe AI will be a big part of this, and that helps you do that more rapidly and more safely. So they all have a place to play. We just, as a business, as an industry, need to continue to keep an eye on making it useful.
Useful. Yeah, that is the huge factor. So I told you before, like the department I work for just got the Explore IR, and so I do want to pick your brain about it for a little bit, right? So obviously gas phase FTIR, don't have to tell you that, but for the listeners, but it also is quantitative. Talk to me about that sensor technology that allows you to quantitate now these gases, not just identify them.
Yeah, sure. So spectrometry in general is quantitative. What's that mean? That means when you measure a chemical using spectrometry, the intensity of the signal, think of it like the height of the peak, is directly related to how much of the chemical is there. It's inherently quantitative. Okay. So if you know that, let's say, acetone at 500 parts per million, okay, in the vapor phase, creates an infrared peak that has a height of 0.1, okay? 0.1 height equals 500 parts per million, okay? And it's linear, and that's the beauty of it. So now you measure acetone in the field, and the height of the peak is 0.2. Well, 0.2 is twice that of 0.1, right? So 500 times 2 is 1,000 parts per million.
Yeah.
So it really comes down to this magical thing, which a lot of your listeners probably have heard of, is the Beer's law. It's actually the Beer-Lambert law. But when we measure specifically FTIR, as we're talking about with the Explorer, as we measure that data, in absorbance units, and that's what you see on the left-hand side, the up and down axis. The measured signal is directly proportional to the concentration. So what we do, and actually when I say we, the industry, not necessarily 908 Devices or Red Wave prior to that, is measure vapors and gases in the laboratory at known concentrations. So you set up a big old contraption, say, okay, I'm going to generate 100 parts per million of acetone today. I'm going to measure that infrared signal, and I'm going to put that in my library that 100 parts per million of acetone looks like this. That's what we call a quantitative library, okay? And then in the field, when we measure an unknown concentration of acetone, what we do is we take that quantitative library signal and we basically adjust it until it overlays the measured signal, and we do some very simple math. And we just multiply to figure out, okay, based on the quantitative library, what's the actual concentration of the acetone in the environment. Okay? It's linear. It's based on Beer's law. And a couple of the beautiful things about it is you only need one quantitative spectrum because it's linear. And once you have that one signal, basically your device, your Explorer, is permanently calibrated to, in this case, acetone, or to any of the other 5,000 gases where it's calibrated to. So you don't have to do continual calibrations. It's inherent to the library data. Now, there's a caveat. There's a trick, Jake. When I say it's linear, that is only within a certain range of peak heights. Okay, so think of it this way. So try to get my hands on the screen here.
Okay.
Okay, so here's my baseline. And when I'm starting to measure acetone, okay,
yeah,
I just see a little bit of a peak.
Yeah.
Okay. And then as I'm measuring it more and more, getting more and more, my peaks get higher and higher and higher and higher and higher. Okay. So the peaks get higher as the concentration increases. Problem is when the concentration gets too high, now we say that the acetone signal is saturated.
Okay.
That means that basically when we're doing an infrared measurement, we're shining light through the chemical. Okay.
Yeah.
And we're measuring how much light gets through and that we can see. Well, if not enough light is getting through, we can't see it, and then we can't make a reliable measurement. So when the Explorer, and what is fantastic about it, is it does this work for you. When you make a measurement of a gas or vapor, and the Explorer pops up and says saturation detected, that means it got a little too much of the gas or vapor, and it's got to dilute itself a little bit just to get those peaks right into that magic window, what I call the Goldilocks range.
Do all the chemicals have the same ppm for saturation, or is it different for different things?
It varies wildly. It depends on how well they absorb.
Molecular size kind of thing, or what would be
not so much size, but what we call the absorbance coefficient. Basically, how Mother Nature dictates how well their electrons will interact.
Okay.
So some things absorb very weak. I'll give you a good example. Hydrogen sulfide, it absorbs very, very, very weakly. So it takes a lot of it in terms of parts per million to saturate. Something like water absorbs very, 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 very strongly, or carbon dioxide, or methane is a better example. So it doesn't take much. It could take just a few hundred parts per million to saturate, where something can take thousands of parts per million. So it depends.
Is that why historically water causes problems with FTIR?
Yeah, because water's everywhere. Yeah. It's everywhere. So yeah, the Explorer takes into account that saturation, dilutes the sample right into that Goldilocks range where the peaks are high enough that you get a good signal, but not too high that it saturates the signal. And I want to be very clear, saturation, don't think of it like that it spoils the cell or does any damage. It's just the peaks are too high. Just got to dilute them a bit. And then we can get a quantitation just by doing that simple math based on Beer's law. But yeah, water vapor, the problem is it's everywhere. Infrared is a great water detector. So historical approaches to dealing with it, we're basically trying to subtract it out, say, okay, here's water, let's subtract out this reference and get rid of it. But that didn't really work very well. And what RedWave did, and now 908, after the acquisition, what I thought was so beautiful, both in terms of water and carbon dioxide, which are just ubiquitous in the atmosphere. They said, we're not going to fight it. We're just going to accept that it's there, water vapor and carbon dioxide. Not only are we going to accept that they're there, we're going to accept that they change. You might do your backgrounding in a nice air-conditioned, building, and you might step out, somewhere in Dallas, Texas in August where it's, 85% humidity. It's going to change. So they built this model called adaptive atmospheric compensation, which basically says we're just going to treat water vapor and carbon dioxide as mixture components. They're there. Why ignore them? Now, we're not going to report water vapor as a mixture because who cares what the humidity is? We're going to treat it like that, model it, and then we're only going to report the chemicals we care about, like the acetone or the other 5,600 things in the library. Carbon dioxide, we do report. When I say we, I'm still stuck into that.
I think they'll be okay with you saying we. You put enough time in to get a we forever, I think.
I just love those devices so much. Again, having done FTIR in the aerosol and gas phase as a graduate student. But the carbon dioxide is reported because it can be hazardous at high concentrations, especially in confined spaces. So that's how it works, and it's pretty darn effective.
It's sweet. And when you were going through school, could you have ever fathomed that the state of technology would be where it is now?
Absolutely. I knew exactly where things would be 25 years into my career.
Exactly. But I mean, in terms of the fact that when you were getting into this, you had virtually room-sized equipment, and now it's a very portable, like in your hand, and probably better specificity and better, all these things. I have to imagine that it's relatively mind-blowing to see the progression of technology in just your career thus far.
Yeah, Jake, as a graduate student, I think I mentioned that the FTIR I worked with, it was a high resolution laboratory FTIR, size of a refrigerator. And then I went to this conference during my spring semester when I was getting ready to defend my thesis, looking for a job, and saw this company, Sensor Technologies, and had this traveler on a little shelf in their booth. And I went, wait, that's an FTIR? Now, this thing would fit in a suitcase. So when I say portable, but compared to what I was used to, did I ever think it would get to where we are now, where they're handheld? I mean, you look at something like the True Defender from Thermo, literally handheld, and even the Explorer from 908, handheld for gases. No. But I will tell you, it over the course of a couple plus decades, the things that have happened, and I've talked about this in recent workshops, it's not that we didn't, and I say we as an industry, didn't want to make things smaller and more powerful, but think of the enabling technologies, the processing and the microcircuitry to do more advanced algorithms in a handheld. Battery, and that's an area, batteries that are still evolving in terms of battery lifetime and all that. 5-axis CNC machining with diamond turning. You can create optics very small with very high precision and high reflectivity. You couldn't do this 20, 30 years ago. So that has allowed us to do things as an industry that we couldn't even envision when we were doing this stuff back then. And again, I hope I'm around for another 25, 30 years to see where things go from here.
Yeah, and the obvious segue at this point is talking about the future, but I do want to. I have more questions inside of another space, and maybe you know about it, maybe you don't. I don't know if you've done any work. Have you done any work in laser spectroscopy, like in terms of like laser methane spectroscopy?
Actually, I have.
Of course, you have. Because that technology, so we just got the LZ30, like 2 years ago, and it's awesome. It's unbelievable for especially the most common runs we're running are natural gas releases, stuff like that. And it's just, it opened up a whole new world of the ability to, get readings at range. And the first question, so obviously that technology as a whole is insane, but is it as simple as putting another spectrograph in there and now having laser pick the thing spectroscopy, or does it work specifically for methane for some reason? And it seems like, well, cool. Let's just like upload this library with 5,000 different spectrographs, and now we have this unbelievable, thing. True or false?
So, I did laser spectroscopy as a graduate student. When I mentioned the aerosols, which we measured with FTIR, the condensed phase part. We used what was termed an infrared tunable diode laser to measure the vapor phase in equilibrium with the particles. So the beauty of lasers is they're very narrow line width, meaning that you can focus in on, when I say focus, not optically focus, but spectroscopically on one little tiny part of the spectrum that you care about. In case of methane, it's those very intense, sharp peaks there on the right-hand side of the infrared. And it's very sensitive laser spectroscopy. Now, at the time, this was, again, the late 90s, early 2000s, there was a technology coming out onto the market called quantum cascade lasers. Now, for the infrared, mid-infrared. The reason that was exciting is the infrared laser that I used operated at 4 Kelvin, or more like 10 Kelvin in that range. So you had to keep it cryogenically cooled, because these are semiconductors, and you just have to get them down cool enough so they can emit. Well, quantum cascade lasers are quite different. They operate at room temperature, or a temperature stabilized area around that range. So a few years ago, I worked for a company called Block Engineering, who was and still is working in the area of quantum cascade lasers for commercial and even for some military applications. And the thing that's important there is the availability of the laser itself. And for mid-infrared lasers, they are based on semiconductor technology. They're basically chips. So similar to like a microchip you'd have that runs your computer, okay? But they're very tricky to construct. And think of it this way: unless you make millions of them as a manufacturer, they're very expensive. But this goes back 15 years ago when I was doing that work. Again, things have evolved. But the nice thing about lasers, they're very sensitive. And then you can get detectors that can detect mid-infrared radiation. But lasers can go very long distances. And can measure things like methane over very long paths, pretty good sensitivity. and they also are much higher resolution. So think of the digital cameras back, in our early days. How many megapixels, do you got? Yeah. Well, the more megapixels, the clearer the image, the better you can see tiny little differences. Think of your 4K TV and an 8K TV. Well, spectroscopy is very similar, where FTIR has a certain resolution, meaning how close together are those data points, then how well can we tell two things apart, which are very similar in terms of peaks. Lasers can do that pretty well because they can be pretty high resolution sources versus an FTIR source. So, and then you have the detectors. So, and then the way that you, if you will, scan the wavelengths. Lasers aren't done with. So in FTIR, you have this moving mirror mechanism, which basically scans the infrared light coming off the source in time. With those laser systems, you use something that's a dispersive system or an optical non-dispersive system. So they can be no moving parts, they can be smaller, less power requirements, all that. So a lot of advantages to them. Again, I have worked with them in graduate school and more recently, and I'm glad to see there are some commercially available products coming out in that regard. But in the end, you mentioned libraries, it's still just infrared. Infrared is infrared. It doesn't care what the source is, whether it's a laser or a light bulb. It doesn't care what the detector is. That's Mother Nature.
So theoretically, there's no limiting factor other than the fact that obviously there's an industry that pushes this idea of wanting methane detection, but there's no precluding factor in the technology that wouldn't allow a company to make a laser detector that has a library that could identify a host of things.
It's not a technical issue.
Yeah.
I believe it's more of a commercial viability issue. And I'll give you a good example. I actually was talking with Bobby and Mike about this several weeks ago about residential natural gas detection. And where I live in West Virginia, every home has natural gas. We get it straight out of the mines. In other parts of the country, a lot of natural gas, and your homes have it. Now we have CO and smoke detectors, but what we rely on for natural gas leaks is the odorant, right? The mercaptans. You smell gas, well, get out of the house. And I'd heard of an incident, not in this state, but some folks I know nearby, where there was a home that exploded from a natural gas leak. And it got me thinking. That's why I reached out to Bobby. And so in principle, you could have a residential natural gas detector, based on, it could be a laser, it could be non-dispersive infrared, it could be a lot of different types of things, which just are, if you will, tuned to natural gas and can even fit the natural gas data to give you a concentration and an alarm, just like your CO detector alarms when it's above some threshold. But to make something that's viable for a residential application where you go to Lowe's and pick it up for $30 or $50, that's more of the challenge. And so I'm curious to see, I'd like to have more discussions with folks about this and see where things go in that regard. Because natural gas isn't going anywhere. Yeah, we're going to be mining it and using it for a long, long time. I did work in an area. This isn't laser spectroscopy related, but just to give you a little more flair from my background, spent a year working for a company that does hyperspectral infrared imaging. And basically, the cool thing they were doing and still are doing that I was working on is flying aircraft over natural gas transmission pipelines and collecting this data. This is passive spectroscopy, so there's no source. You're just relying on the heat from the sample contrasted to the heat of the background and getting a spectrum of methane as you're flying over these thousands of miles of pipeline in a little Cessna with this little spectrometer window out the bottom, and using that to look for leaks.
Wow.
So natural gas leak detection is something I'm very curious about, and would like to learn more about it, especially as it relates to residential application.
For sure. So as we start to look to kind of wrap up here, I do want to get the Mark Norman view of the future. What is, I mean, I would imagine you probably know some things that you can't talk about, but of the things that you can, what does the outlook for chemical detection look like?
What I see, as I alluded to earlier, is most likely incorporation of AI to do a lot more information processing and information communication that is much more effective and much more useful to all sorts of responders on scene, in whatever the responder type might be, whatever the scene might be, to take more of a holistic approach versus having these disparate boxes and trying to figure out on your own what tactical decisions should be made. So I think that's a big one. Size and weight sort of have a limit where they become less useful, but you'll certainly see things like battery life with battery technologies getting better, but also with things like all the other electrical components being less power hungry. So batteries last longer in your electronic devices. And then I do see a more of an emphasis going forward on things like safety. So we do chemical identification, hazard identification, but some things that are more related to addressing things like firefighter health, soldier health. It's not just firefighters, it's soldiers in the theater of war. And what can we do from a chemical detection perspective, even after like structure fires, and for the public, and all these things that are in the atmosphere. So sort of a progression towards what can be made available for the safety of the populace and the responders from an analytical chemistry perspective. So those are some of my thoughts and some of my sort of projections based on what I know about the industry, where I see things potentially going over the next several years.
Awesome. Well, thank you for the time. It's been a pleasure to talk to you. So much information, so much intrigue in the industry, and thanks for making devices usable for the community I'm a part of. I appreciate the work you're doing.
Thank you very much, Jake. I've really enjoyed it. I'm glad we finally got together. By the way, before we go, when you see Bobby and Mike, see if they remember what this is.
Is that a prison shank?
Well, just ask Mike.
Okay.
I'll give you a hint. It has to do with this. You see, I got my little props.
Okay. Oh, I know that thing.
You got this. You know what that is? Okay. And then also, speaking of batteries, one of these. So. Okay.
So you're blowing up something.
Well, not anymore, but we did. But if I may, again, I really appreciate this opportunity. Sure. And if anyone wants to connect with me in any way, best thing to do is find me on LinkedIn. Under there is Mark Norman, PhD. And I do have my consulting, Centerburst Consulting business that I maintain. And I'm happy to connect with people if I can provide any form of my services or just expertise or knowledge to those folks. I'm also on Facebook, but unless you want to, see what my girlfriend and I had for dinner the night before.
And we'll tag all that stuff in the bio underneath the video and the podcast and make it accessible for people. Once again, thanks, Mark. It's been a pleasure. Hopefully we'll do it again at some point. I'm sure there's a billion more things we could talk about. But yeah, awesome, man.
Thanks, Jake. I love your show. Love what you're doing. Really appreciate it. And I hope to see you in person sometime again soon.
Yeah, absolutely.
All right.